Hi everyone. First of all, I cannot speak very loudly today because I have a cold, so I'm sorry if the ones in the back don't hear me very well. I'm going to talk to you about a paper titled Knowledge-Guided Disambiguation for Large-Scale Scene Classification with Multi-Resolution CNNs. I'm going to do a brief introduction to the problem. I'm going to talk about the contributions of this paper, very briefly about some related work, and then I'm going to talk about the things they propose that are multi-resolution CNNs and the knowledge-guided disambiguation. Then I'm going to comment the experiments and results and finish with the conclusions. Well, scene recognition is a fundamental problem in computer vision. Some of you have worked with this, I believe. And the main thing here is that it is defined by multi-level information. You have to take into account the local objects, the global layout, the background, the environment, and how these elements interact between them. So this makes the concept of scene a very complex one, and it is also quite subjective. So this makes this a very challenging problem. Fortunately, some large-scale datasets have appeared in the late years, such as Places and Sheng 397, but these datasets have some problems that I'm going to comment later. The first of all is that there is visual inconsistency, which means there is a large intra-class variation. These images here, the four of them, they all belong to the same class, which is cafeteria, in the Places 365 dataset. As you can see, they are all very different. And it's difficult to extract the common information here. The second problem is the level ambiguity, which is the opposite of before. That is, that there are several classes that look very similar between them. In this case, two of these images belong to the class office, and the other two belong to office cubicles. As you can see, they are very similar. The two on the top are from office, and the two on the bottom are from office cubicles. But you know this because I'm telling you. So, and of course, this is very easy to confuse, even for humans. So what is the contribution of these guys here? They propose a multi-resolution convolutional architecture to capture multi-level visual cues of different scales. And they also introduce knowledge-guided strategies to solve these problems of ambiguity. They tried in two different ways, by extracting knowledge from the confusion matrix and by extracting knowledge from extra networks. This last one is quite interesting, and I'm going to explain it further later. Well, of course, there has been previous work about this. Scene recognition is a problem that has been on the table for a long while, and several authors have considered a spatial layout, such as Limin, I don't know how this is pronounced. Parisi et al. Well, we have the reference at the end if you can read, if you want to read further about them. Some of them have tried to identify mid-level discriminative features, and of course, deep neural networks here are on the table too. But the thing is that for deep learning, you need a huge training data set, and this was possible to apply in this case when the large-scale data sets such as Places were created. First they proposed Places, and then they enlarged it and introduced Places 2. And recently, instead of Places 2, they are proposing to use Places 365. Places 2 has 401, I believe, classes, and places 365 now has 365. So it's a variation of this.
So it's less.
I don't know because I think that some classes are merged. I haven't analyzed it deeply, but for instance, I have found that in places 2, you have the classes car back seat and car front seat, and in places 365, you have simply car indoor. So I'm not sure.
The images are the same, the 10 million images.
I don't know. I'm not sure how they adapted this or if they deleted something, but it's a variation. I don't know what changes they made. Of course, image classification has been used with neural networks. There are several known architectures such as AlexNet, BGGNet, RiseNet, and Inception Network, which is GoogleNet. And some regularization techniques have been proposed, such as dropout, smaller convolutional kernel size, and multi-scale cropping. And some optimization techniques have been proposed too, such as batch normalization and relay backpropagation. Here they use an inception network with batch normalization for their architectures. And knowledge transferring has been an active topic recently. It was first proposed, I believe, in 2006, but the paper of Busila et al. And then it has been applied in several domains. For instance, it was used to compress model ensembles for fast deployment, to help train on deeper networks with multiple stages, for domain adaptation, of course, and for real-time action recognition in videos. So, what these guys did that was new? They proposed a multi-resolution convolutional architecture, and they based themselves in that some scenes contains several features in several information in different scales. So they proposed to combine two networks that received images of different sizes. And they based both of them in inception batch normalization, batch normalization inception, sorry, and they trained two networks independently. The first one received smaller images, 224 per 224, and it was a normal batch normalization inception. And then used a second network, what they call fine resolution convolutional neural network, that received larger images. And they added two more convolutional layers. And they were trained independently, and the outputs were combined. Here is the architectures. This is a normal GoogleNet with batch normalization. And the second one, as I said, they are adding two more convolutional layers. Then, for the knowledge-guided disambiguation part, they propose to extract knowledge from the confusion matrix, which means they train the network, as usual, and then they computed the confusion matrix with the validation set, in this case of places. With the confusion matrix, you get the similarity between classes. The classes that are more confused are more similar. So they computed the similarity matrix, and from that they defined a threshold, and they merged the classes that were similar above that threshold together. And to classify, they say that they divide the probability equally among all the subclasses. They say this works. I'm not sure how they do this, because I suppose that it would lead to ties, but they say this works and they got good results, so I cannot argue. And the second thing that they proposed for knowledge-guided disambiguation is using knowledge from extra networks. They propose to use another network, train it with another data set, such as ImageNet or Places, not Places to Places, which is smaller, and create a soft label based on the outputs. The thing is that they get an image, for instance, of this classroom, and they pass it to a network trained on ImageNet. And from ImageNet, they will get, I don't know, the class blackboard, computer, table, and chair, for instance. And with that, they will get the soft label. The thing is that they can get the intra-class variability well with that because they only depend on the single image. And the soft labels for similar classes will be similar, but it will be different for different images in the same class. For that, to do this, they train using the following loss function. And as you see, they use the hard label, which is the normal label you will use to classify, and the soft label obtained from the extra network. It's not very clear here, but I believe they use the direct output without training anymore as what they call the soft label obtained by extra network, and then they do some process of fine-tuning to use the predicted soft label because there will be no point of calling it different if they are using the same. But they are not very clear on this point. Finally, I'm going to comment the experiments they made and the datasets they used. They used ImageNet and Places, basically for the extra networks, and Places and LSAN as the objective datasets. And then they used SAN 397 and MIT Indoor 67 to test the generalization. Well, using the multi-resolution convolutional networks, they tested it against AlexNet, BGGNet, and the two networks separately for the datasets of ImageNet, Places, and Places 2, and in the three cases, they got a better result. I don't know if you are seeing this well. Can you read it? I don't know if I can zoom here. ¿Puedo hacer zoom, Mark, de alguna manera? Well, they outperform it for 2%. Well, there is a significant difference. It's better. You have to believe me. And then they tested the knowledge gathered disambiguation. Here you can read it. Okay. And they tested in several models. That's the normal batch normalization network against the deeper batch normalization network and different combinations. And they got that the best was a fusion of the deeper batch normalization inception network and the deeper batch normalization network with SIN networks. When they say SIN networks, they mean that they are using an extra network trained on Places. And when they say they are using object networks, is that they are using a network trained on ImageNet. And of course, it works better with Places than with ImageNet. I guess that because it is a closer topic. And they ran for the Places challenge. They got the second place last year, and they got a better result after the submission. And this year, they improved the result further. I guess they made some changes too, but they didn't bother to explain them in detail. But they got a better result, but still a worse classification. They are in the 4th place. Also, they ran for the LSAN challenge. They are the SIAT team, and they won it. So they got an amazing result on that. And finally, they tested it against Mighty Indoor and Sun 397, where they outperformed all the other methods by like 2%, well, a bit less in case of MIT Indoor 67. And this was from October, so I think they are the state of the art right now. And basically, as conclusions, we can say that their knowledge-guided techniques are able to effectively not solve but improve the problem of ambiguity, and that with the multi-resolution CNNs, we're able to capture information in several scales. Also, they got very good results in several challenges, but as cons, we have to say that some classes are still very confused, such as supermarket, pet store, and toy shop from outdoor, downtown building, skyscraper, or conference room or classroom. So there is still room to improve, and ambiguity is still a large issue, so there is still place to work on this. And here you have the reference in case you want to read something else about any of these topics. We have many more about many other things. I've referenced almost everything I told you. So if you have any questions.
There are a lot of similarity with several people that are working here, so
I have some questions about the interclass variation. Not really the class variation. You say that one of the main problems is the confusion between different tags. Like an office can be confused with a box, working box, and what they do is they just do a confusion matrix and they merge all these tags together. So I think,
yeah, no, but not all. They define a threshold that they don't specify which was this, but I guess they did some experiments about it, and they got to merge some classes that are very, very similar together. For instance, as I said before, the office and the office cubicles, and baseball field and baseball stadium. There are some classes that if you look at them, you as a person cannot tell which is which.
But my question is, how do they use this information afterwards to, once they merge it, let's say they merge classes, how do they use the information of similarity to predict the correct class?
So you mean that they get classified as superclass?
Or do they use this for something?
Yeah, they say that when they have to transfer in this case, the 372 super categories to the 401 original categories, that they divide the probabilities equally. And I commented before that I thought that it could lead to ties, because if you get the first category of super category A, for instance, and super category A is office and office cubicles, how do you get the final class there? I don't know.
this is a question. If you have 0.5 and 0.5, so which is the final?
Well, actually, I want to apply this, so I put in contact with the first author, and I sent him an email asking about this exactly, because I'm not sure how to do this. He still hasn't answered, but I'm waiting for it.
He answered the first time.
Yeah, I sent him an email saying, "Hey, will you bother if I ask you about this?" And he said he would be glad of, helping me or whatever. And then I sent him asking this, and he still hasn't answered. But this was like yesterday, so.
In fact, we were trying to do this with Eduardo and Decker, yes, but we're not able, but didn't have time to finish this work, but try to represent this hierarchical representation of classes. So probably you can have one mixed class and then another classifier that is focused just on this class to separate.
I don't know if they do this
No, they
in
don't.
several
They
levels.
just assign the half of the probability to one, the half probability to the
Yeah, but I don't know if they do this recursively. I mean, I don't know if they get a superclass A, and in the second iteration they merge that superclass A with another class so that you have a taller hierarchy. I don't know. They don't give the example here,
It
but
seems much more simple. At least what is written in that what we put here is that you have, if we instead of having 400 categories, you have 372 categories where some of them are combinations of categories. And then when you have for the combined category, the score is 0.9, so you put 0.45 to one and 0.45 to the other. This is what is written here. So
yeah, this is what they say they do.
yeah. The point is that if you do this in a hierarchical way, if you have the classifier for the common category and then go bring this and then separate this sequentially, so you can propagate error. So an alternative would be the echo, right? For example, where we create a different combination of, if you have A and B, which are very complicated to make, so you can construct different combinations, A and B, A with another one, B with another one, and then you create a code in order to separate. So you mix different classes in order to help to the classifiers work better. So, but also we well, it wasn't just but I was wondering that is, for example, for the other, when you mix the different networks. So can we go to this?
Yes.
Here, no, before the previous, this one. So this is what probably you are trying also to estimate, right? Because you have also and other people also. So my question here is, well, you say QI is predicted soft level and FI is also soft level. So what is the difference between QI and FI?
That's another doubt I have, because they say they use the predicted soft, the soft level obtained by extra network, but I guess they do some process of fine-tuning or something, because there wouldn't be no point of talking about the soft level obtained by extra network and then the predicted soft level. If you do nothing, it is the same. So I guess this training is combined, and they also update the extra network somehow.
And still there is it's the relation between both of them should be in some way estimated, right?
But I'm not sure about this. This is one of the points where I have doubts.
Right, so we use this as features, not in the error in the loss function, right? So usually what we do in SR clustering, we use these labels as features in order to optimize the left term.
But I think that this is something different. This is just for calculating the loss.
Yes.
For training the model.
Yeah, but you should, in order to estimate this loss, you should have the relation between both terms. Right.
Well, here the relationship is just a weighting parameter. So they just weight one of the terms and they sum them together. So, I mean, I think that this is just for calculating the error of their network, given an additional network that provides another answer.
Yeah, but this error depends on the, for example, the objects that are obtained by Einstein, right? So in order to say that the objects share is contributing to the loss, the category kitchen, you should define that you should have this relation between care and kitchen.
Well, I think that they just learn it. I mean, they don't have this specific relationship, and they hope that all the images that contain cafeteria, for example, all of them will have chairs and will have tables. So it's a knowledge that the model should capture without defining any relationship manually.
How other people understand it? Did you read the paper?
I think they try to learn this relationship, as Max says, instead of learning it manually.
Yeah. Okay. Other questions? Where is the article published? Where is the article published?
It was I found it in the Places Challenge. So I don't know if it got published somewhere else about archive. I don't know how it's archive. I didn't find it in any conference. No, what
And
María
is there
mentioned.
any code, any public code? And is there any public code for this?
I don't know. I'm not sure. Not an expert in this yet.
Do we have other questions?
I don't have a question, but just a discussion because we discussed it last day with Peter and Mark. We were thinking also not in places but in food-related problems, so to recognize a different kind of foods. And we were thinking to make also this hierarchy, but build it for an expert. Not let the classifier do it by itself with the confusion matrix. So we were thinking about that, but also we thought about let the network do it by itself, just like they did. So I don't know what is better to do. I don't know.
Well,
It's a discussion for everybody.
they propose this because they think that capturing all this information manually is very complicated because this dataset is huge, and this Sheng classification is, among other things, subjective. So maybe I don't know in the case of food type hierarchy, but in the case of a Sheng, for doing the hierarchy, my hierarchy could not be the same as your hierarchy.
Yeah.
So they try to do it with the data, which are the facts, trying to be more or less objective.
In this line, I thought that, in fact, well, this is very possible, probably it makes sense. Instead of mixing the categories where the classifier is mixing this, and here's the biggest problem, probably to mix when different user give different labels. So in this way, you have really the ambiguous classified that experts. The point is that sometimes it is very, very costly to estimate, but even if you have some of the annotations and then you get an estimate, so you can think about ambiguous categories due to the users. Just theoretically, the classifier should try to imitate this, but not always. Okay. Do we have any other comments? Okay, so that's all. I would like to say that if we want that these seminars are useful, it is very important that all of you read the paper and prepare some questions. Right? Because otherwise, it is all past, go to YouTube and see a presentation. So if it's just to hear the presentation, we send seminars, so the next topic we have here